Welcome back. We're going to rotate this region between the graphs of f of x equals x squared and g of x equals square root x around the x-axis, and you're going to notice that if we do that, it'll generate a solid that has some empty space inside, meaning that if we slice perpendicular to the axis that it rotates around, you're going to get slices that would be washer slices. And so I like to actually take a try at drawing those washers first in the picture. And let me grab my yellow pen or my pen here. Hopefully you can tell which of these curves is which. The green is definitely the function x squared. And then the red is definitely y equals square root x. So it's important to note that the square root x is the upper function in this one compared to the x-axis, and the green is the one closer to the x-axis. Remember, we're going to spin this, picture spinning this around the x-axis here. So imagine picking a little slice. Let's make it a color we can see. If I were to make a slice perpendicular to the axle right there, like a little rectangle, and picture rotating that rectangle around the x-axis, the part touching the green curve is going to make a small little trip around a circle there. And the part at the top of the rectangle is going to make a little bit of a longer trip around. Okay, and then the thickness of that rectangle causes this to be a very thin little washer-like solid there. And picture now there being hundreds of those little slices going across this region that begins at the point 0, 0 and ends at the point 1, 1. Okay, so our idea is to set up a definite integral where we can tell in this interval, since we're going around the horizontal axis, it's going to be a definite integral that's with respect to x. So the ending will be dx. And then our template, remember, is pi times each radius squared. So the key here is to look at the picture and determine how you're going to measure each radius. In fact, I'm going to make a little room for this by moving these down a little bit. What we normally would do first, kind of as some introductory work, is to figure out how do I measure each of these radiuses. And in a picture like this one, since we are rotating around the x-axis, all I have to do is measure from the axis of rotation, which is y equals 0, up to, and the largest radius is the point furthest away, which is the point on the red curve. And so square root x, the expression for that curve, minus the axis, which is 0, is the expression for the large radius. And then the small ring has a radius measured from y equals 0 until I get to the lower curve, which is x squared. So x squared minus 0, in this case just x squared, is the small radius. And remember, the template in our integrand then is large radius squared minus small radius squared dx. And the interval goes between x equals 0 and x equals 1. This would be an excellent candidate that you should be able to solve without a calculator, because after simplifying the integrand, we're integrating x minus x to the 4th between 0 and 1. So other than to have pi there again, the antiderivative is 1/2 x squared minus 1/5 x to the 5th. And we're going 0 to 1. So what you're going to find out is the only math you really have to do is 1/2 minus 1/5 times pi. And we can make that into tenths and do 5/10 minus 2/10. So the final answer is 3/10 pi, or 3 pi over 10. no units necessary. And that is our volume. Okay, well this time we're going to rotate this region around the x-axis again, and the two equations of this region are given. Hopefully you can tell which one is which. The parabola in green is going to be the function 3 minus x squared. And I'll just go ahead and label that here. I'm just going to label it actually f of x. And g of x equals 2. Of course, that's the red horizontal line. We'll label that one g of x. And we're going to rotate this shaded region that's between the two curves around the x-axis. I like to put my little swirl there to say this is where we're going to rotate around. And so imagine again that if I take any slice, like say, let's say a little rectangle that is within this region, that is between the two curves, and we're going to rotate that around. Or in fact, just picture rotating this whole region around the x-axis first. You would see a silhouette of the red line down here at -2. And this curve would end up kind of being silhouetted around the bottom here. And so now any slice would have an inner ring between these two parts. And then the outer part of this washer slice is going to come around here. Okay, so the center line is, or the axis is the x-axis, and I'm going to take a blue pen now and highlight the small radius, and then the large radius from this curve all the way to the bottom. I know we're kind of getting kind of full in there, but we can now notice that the large radius, the largest circle, has a radius measured from the x-axis, which has a y value of 0, to this green parabola, which has a y value determined by 3 minus x squared. So if I subtract those two distances, that's the large radius expressed in terms of x. And then on the other side, let's look at the small ring. It's being measured from the axis, x-axis, which is y equals 0, all the way up until I get to any point on the red line, which always has a y value of 2. And so the small radius this time is a constant 2. This interval in the measuring in the x direction starts at -1 and ends at 1. And so our integral for this volume is going to be an integral from -1 to 1, the large radius squared, minus the small radius squared, times pi. Now to solve this integral, the best thing to do would be to expand out the parentheses and collect some like terms. So for example, 3 minus x squared times 3 minus x squared is now going to be 9. If you FOILed it all out, it'd be minus 6x squared plus x to the 4th. And then we're going to be subtracting 4. So ultimately, if you needed to solve this one without a calculator, here's how I would probably write it at the end here. 9 minus 4 could be changed to a 5, and then minus 6x squared plus x to the 4th. And this would be the final setup. You could now take the antiderivative of this, plug in the -1s and the 1s, and you could get your volume. One other thing to note about this one, and it doesn't happen every time, but this time notice because of the parabola and the line, this pink region actually has symmetry across the y-axis. So one way that could make this problem go a little bit quicker now that you've set it up this way is to notice that if I had taken the region just from 0 to 1, we're going to get exactly half of the volume because that is half of the area of the pink region. So an alternate way to set this up is to change your integral to 0 to 1, keep everything else the same, and then just notice that's only going to give you half of the volume, so we've got to double and just put 2 pi in front instead of pi. So this could be the setup as well. Just take 0 to 1, but noticing that's half of the answer, so we're going to double it at the end. And okay, last example for today, and this time we're going to revolve this region that I've shaded once around the y-axis and then again around the x-axis. And what I want you to pay attention to in this one is as we rotate around the different axes, thinking about, would this create a solid that would slice into washers, or would it create a solid that would slice into discs? The main way you tell is if you were to rotate around an axis and notice that the solid object would have some open space inside it, you're going to get washer slices. If you notice that it does not have any empty space inside it, you're going to get disc slices. So that's part of what I want you to be thinking about as we draw this. So I'm going to try and draw around the y-axis first. I'm going to put my little rotation arrows there. And if you want to picture each part of this region rotating around this vertical line, for example, then the line x equals 2 is going to end up having a silhouette kind of over on this side at -2. This vertical line, this slanted line, is going to have its kind of outline in quadrant 2. And now let's make a slice here and rotate it around, so you're going to end up seeing your washers right here. See, now this does have some empty space inside it, so that's why you have the washer slice. And this time noticing that your washers have a radius measuring in the x direction that depends on the y value. So for example, I'm drawing mine at about the y value 2, and the smallest ring in this washer always is from the y-axis to that sloped line. And then the larger radius is going to be from the x-axis, or the y-axis, sorry, out to this vertical line. Okay, so one thing I'm going to note in the work here is this does make washer slices, and I need to note what the large and small radius is. So for the large radius, it's going to be in terms of y, because this is from the x, for any value of y, it's going from the x value 0, which is the y-axis, out to the x value 2. So the bigger x is the 2 and the smaller x is the 0. So 2 minus 0, or just 2, is going to be the large radius. And then the small radius is measuring from x value 0 out to the x value of this line. Now notice we haven't done anything yet with that equation. Because we're going in this direction, this equation needs to express x as a function of y, and that can be done by dividing by 2. X would be 1/2 y. And so we're measuring in this small radius from the x value here to the x value of 0. So that's going to be 1/2 y minus 0, or just 1/2 y. And so our washers are going to go in the y direction from 0 to 4, because this is the point 2, 4 up there. So from 0 to 4, the large radius was just the 2, and the small radius was 1/2 y, which you could go ahead and write that as y over 2, and then times pi, and this is an integral with respect to y. So I could finally, in fact, let's move this over a little bit to make a little room. So I can write it one more time. Squaring both of the expressions, I could make this integrand 4 minus the quantity y squared over 4 dy is from 0 to 4. Another one that wouldn't be too hard to get the answer without a calculator if you had to. Now I'm going to erase what I drew in this diagram So I can start the drawings and labelings for part B, which is to rotate that same shape around the x-axis. So let's erase my washers from the first part, and let's try and rotate this around the x-axis this time. I encourage you to first think about, if I were to rotate this triangular region around the x-axis, do you think it's going to create a disc slice or a washer slice? And so if I were to draw the outline of the triangle, rotate it around into quadrant 4, notice there's no empty space or no unshaded space between the triangle and the axis we're rotating around. So that means there is just going to be that solid disc slice this time, no washer. And so let's make a note of that. This is going to make disc slices only this time, no washers. And the radius of that disc is measuring from the y value 0 to the y value of this slope line, which is going to be called y equals 2x this time. And so the only one radius you're going to have is a function of x, and it's the distance from y equals 2x to y equals 0, or just 2x. And so back to discs, the integrand is just pi times the radius squared. We're going around the x-axis or horizontal axis, so the integral is going to be pi r squared. And now we're going with respect to x, the limits should be between x equals 0 and x equals 2. And so again, to rewrite it so that we can actually solve it, let's square this out and just get integral of 4x squared. Again, not a hard one to do without a calculator if you had to. But so we're going to actually, just to save time in the video, we're just going to stop at the setup of the problem because that's the main thing here.